Hi, this is Ajit. Welcome to Step by Step Data Science tutorial. So today we are in part 5, Regularization in Logistic Regression. So before starting this lecture, I would recommend you to watch part 4, which describes about logistic regression, because we will be using the equations from part 4. So all the equations we will refer from part 4 to write in part 5. So I would highly recommend you to watch my part 4 lecture. So we will discuss in today's lecture the concept of regularization, overfitting, underfitting issues, and the how regularization help us to handle those cases. So we will write all those equations from scratch in Jupyter Notebook. So let's start. This is my data set, and this is my data. This is my header. So before starting the concept of before discussing about regularization, I would like to discuss about overfitting and underfitting issue. So if our model does not perform well on both training and test dataset, then we have over underfitting issues. Let's say, for example, so our predicted line is this, and should be the case of underfitting because the prediction is no more close to our module. So this can be the case of underfitting. And what would be overfitting is if my predicted output is output is something like this. If we have our output something like this, then this is the case of overfitting. What this line means is it is the model is trying to fit each predicted line, and due to which we see an overfitting issue. And what would be our good fit if we have an output something like this? This would be a good fit. This would make more sense once we start visualizing and implement regularization. So what is regularization? So regularization is something to address overfitting issues. So to address overfitting issues, we use regularization. So how regularization helps us to overcome overfitting is it includes all the features are included. All the features are included, but we decrease the magnitude of lambda of theta. So if we decrease the magnitude of theta, then we can avoid overfitting issues. So we will see by implementing the equation that handles the overfitting issues. So we know like our cos theta is I log of 1 plus, this is the cost function that we have implemented in our last tutorial. This is our logistic regression cost function. So if we include lambda and my I from this is j from 1 to m theta j. So if we add this term whole square, so if we add this term in our equation, then we can handle our overfitting issues. So this lambda is our regularization parameter. So if we include this term, we can handle our overfitting issues. This is also known as ridge regression. So if we implement this equation, then we can handle overfitting issues. Now let's visualize my data first. Again, I will be splitting my data into admit and non-admit cases. Equals 1 is for my admit case, comma 11 equals. So this is my visualization. So here we cannot draw a boundary line that I have discussed in my last video, because if we draw a boundary line, we cannot split our data like this. Like if we draw a boundary line over here, so this will not distinguish my admit and non-admit cases, because here we have admit, here we have admit as well as non-admit cases. So what we need to do is, what we can say, like what would be the another option to do, because plotting a boundary line will not give us the accurate result, because our data is splitted in circular form. So what we can do is, we can add a more feature in our data. So if we add more feature, if we add a polynomial feature in our data, then we can do a better prediction and visual, and can give better accuracy in our data. So we can add a decision boundary over here, and we need to add more feature in our data, maybe a polynomial, so that we can include more feature and perform and can fit our model. So the option we see is to include more feature, because if these two feature will not give us the linear line that we can distinguish in our data. So that's the reason we need to add more feature. So now we will be adding more feature. We'll be adding 6-degree polynomial equation, and so that we can perform the logistic regression module and can apply our module. So now we will be adding the polynomial equation with 6-degree polynomial equation. So what does this 6-degree polynomial equation means is, we will include our, suppose, so right now we have data like 0, 1, and something like 0 0.5, 0 0.6, and our output is suppose 1 or 0, suppose 0 0.7, 0 0.8, output is 0. So what we will doing, we will be adding more feature, 6-degree polynomial, which means we will be using 0 times 1, 0 times 2, 1 square, and like xy square, x times y, x times y square, x square, y square, x cube, y cube. We'll be adding more feature based on our two inputs. So let's write a code that adds the polynomial equation. So I will be using all the methods that I have implemented last time for logistic. So let's create a new class for regularization, and I will be using the class of logistic regression, so that I can use the methods of logistic regression. This is the inherent concept that we use while implementing object-oriented programming. So what this in past does is it helps me to create a class. That's why I'm using this. So let's create a function called map feature, and here I will include self, x, and my degree. So what I will be doing is I will be adding a polynomial line to a polynomial equation like x square, x cube, and so on. So let's write the code for that. So my initial will have a copy of my dataset. Let's say copy, and I will insert 1 in my data. We all know the importance of adding 1. We have did this in our last video. One. So what I'm doing is uh, I'm making a separate data frame where suppose right now my data frame has data. So I will be adding a new data frame with my x plus the, because it is a number, that's why I need to add str. So I will concat ij in my x, and I will see like how many, what multiplication we have done. So what will be doing a multiplication for this and this column, so it would be something like 0.5 times 0.6. In one field it would be, so 0 1 0.5 0.6. So another will be suppose x, let's say my I and j, i runs from I runs from 0 to 6, and j runs from suppose 0 to 6. So for for every iteration I will concat x in my data frame, that x plus str plus I plus j, which means x0, x1, x2, 0, 1, 0, 0. Okay, maybe 0 1, 0 0, 1 0, 2 0, 2 2, 2 3, and we'll be doing multiplication 0.6 whole square for one column, 0.5 times 0.6 whole square for another column. So I will be adding more feature in our data. So why do we need to add feature? Because the data is in ellipse shape, like it's been distributed in ellipse shape like this. So here we cannot add a decision boundary. Simply that will not distinguish my admit and non-admit cases. So we need to add more feature. So if we add more feature, here we have added more feature. So what I would say is, if there is more feature, if there is more than 1 dozen feature, then we need to add regularization. So if you have any module that contains 12 to 12 plus features or 20 plus feature, you should go with regularization. We need to add regularization while implementing our module, because if you don't, it will again have an overfitting issues. So if you have a module, if you have a data set that includes 20 plus feature, and if you are using a regularized classification module or regularization or regression module, go for regression plus this regression module. So which will, what this will do is, this will avoid overfitting. Okay, so right now I will be adding more feature, and my data frame, like I will concat I and j in x, and which will do the, we will take the square of individual term. Hope that makes sense. That's why I'm adding square. This will go from. So what I will be doing is I will be adding np.power of my data 0 comma first I will do I minus j minus power data of 1 comma j. Okay, so let's return this and see what our output is. So this is my class. So this is my class. X comma, let's say 6 degree. I have used 6-degree polynomial feature. So what is my x? X is data of 0 and 1. Okay, okay, let's view my data. So like here we can see once has been added. One is being added because of this line of code. What it does, it creates a column named once in 0 position and append all the 1. So on once column is created, it is been appended in my 0 position. Then we have this is our initial to feature, and like we say, like all the power of 1 times 2, this times this is 0, that's why it's same. So likewise the polynomial, all the feature is being generated. If we look at the same, so we don't need this 2 feature because it's already been included in 1 0. So we can remove this two column 0 and 1. So let's do that. Let's remove 1 comma 2. This is my 1 comma 2 position. So in data 1, drop column data 1 dot volumes equals, volumes is my equals, access is 1 because we are deleting it column wise. My in place needs to be true. Okay, then we will return drop 1. This makes sense. Okay, 2 columns has been removed. So this is the feature that we will be 118 rows, 28 feature. So we can see 28 feature in our data set. Now let's give it this name as x1. So here we can see like we have now we have 28 features. 28 features. So why do we need to add polynomial feature? Because our data was not easily separated by using a boundary line. We cannot separate admit and non-admit data. That's why we usually do visualization and see how our data looks like and whether we can apply logistic regression or not. Like we can apply logistic regression. I mean to say, if we need to include a feature or like polynomial 6-degree polynomial we need to use or not. So that's why we need to have a visualization so that we can see a clear picture of our data. So right now I have included my polynomial equation. Now we have 28 feature in our data set. Okay, now let's write the equation for cost function. So now we have 28 features. So the what regularization do is regularization handles overfitting issues. If we need to use same feature, and if we have more than like I said, if we have more than 10 to 12 features, then we need to include regularization so that we can avoid overfitting. So if you have more than 20 features, like 15 features, go for using regularization, so that we can have overfitting is avoided and we can have a good module. So let's implement cost function. So the cost function self theta x y lambda, let's say n comma n to be made safe. So this is uh, the cost function that I am pulling from my last video tutorial. So this is the cost function that we have implemented in our last function in our last tutorial. Sorry, theta x and y. Now what we need to do is we simply need to add this term. We simply need to add this term. We have already implemented this equation in our last video. So I am pulling those methods that I have done last time by using inheritance, and now I will simply add this equation in my code. So this is what I have written in my last video, and I have pulled that and stored the value in j. Now what we need to do is j equals j plus, so my equation is lambda times theta j square. So j plus, let's say my lambda, we'll give it a name like lambda of coefficient. So now my equation is j plus lambda of divided by 2 times m into summation of theta. We need to note that, sorry, so here my theta is from 1 to j, so we need to exclude theta 0. So this will be my from 1 to n times theta from 1 to n. Let's written j. So let's call this function over here. My cost will be, this is my object dot this class, this method. And here in the pass, let's create an initial theta per theta. So my initial theta will be p dot zeros x1 dot say of 1. Let's pass initial theta, then my x1, y, and 1 for my lambda. So my y is data of 2. Okay. So here we have my cost function. Now let's implement gradient descent equation. So this would be my gradient theta y comma lambda coefficient next dot c. So my gradient descent equation is, so we know that theta j plus alpha g of j theta by d theta. So my d of j theta by d theta is 1 by m. So we know from last video we have derived that my gradient equation is this, and right now what we need to do is, if we take a derivative of if we take derivative of lambda j equals 1 to n theta j square, if we take derivative of this with respect to d theta, then lambda will be out to theta, and then we have 2m over there, so theta, this 2 will be cancelled, remaining will be theta by m, lambda by m by theta j. So this follows like d by d theta of n equals n theta to the power n minus 1. So this will be the remaining, this will be lambda by m theta j. So this is the equation for regularization. So we will add this in our code. This we have already written last time. So this we will call this method, we will call this method from logistic regression that we have already wrote, and then we will add this equation. So that makes sense. One thing to note is this is again from 1, theta is from 1, not from 0. So what I will be doing is, initially I will take a theta 1 that will range from 1 to n, and my theta final will be, I will adding one horizontal stack, I will do horizontal stack and add 0 in my theta 1. This is because this j starts from 1, so I will concat 0 with theta j. So my final will be theta j will be 0, and 0 will be concatenated because my theta, this starts from 1, j starts from 1. Okay, So my theta, suppose my theta 1 is theta of 1 to n. Final theta f, as I said, will be doing a horizontal stack and will append 0 comma theta 1. Why we did this is because my theta starts from 1. So this is my gradient descent equation. This is the one that I have implemented last time. Dot this gradient. So this was the one that I have already implemented. Now what I will do is I will simply add my gradient final will be this plus lambda coefficient divided by m times theta region comma x1 y and lambda is 1. That's a way started and 1 hour. Okay. This looks good. Let's check for let's check. Let's check for lambda equals 10. Okay, this looks fine. Now let's write an equation for obtaining optimum value of theta by using SciPy. We have used this in our last video and we will be adding lambda in our equation. So let's write my minimum cost function. It would be the same. Simply we need to add lambda in our equation. Let's call the function cost function. X of 0 is theta, element is x comma y comma lambda coefficient. Okay, then theta underscore optimal value will be this times x, and then we will return theta. Log. So this is my method. Min cost dot cost function comma initial theta comma x 1 comma y comma Let's give a lambda 1 initial theta. Yes, we so yeah, this is my minimum cost. Now let's predict my output. Predict this I have already written in my last video. Okay, let's generate a score. Score for hybrid. That's 83%. So using scikit-learn logistic regression with lambda equals 1. This is my lambda. I have given 1. So it's matching. So this is how we implement regularization. Now what I will be doing is I will be doing a visualization and I will show you the overfitting underfitting cases. So what I will be doing now is, in visualization part, I will be using a mesh grid and doing a plot for data ranging between -1 to 1.5 up to 50 times. This would be my x, and my y will be from -1 to 1.5 to 50 times using linear line space. And then I will be using mesh grid. So what a mesh grid does is it creates another x by x. Suppose if we use a mesh grid, it will create another matrix that would be of shape 50 by 50. So if I use mesh grid, my x by x, if I use a mesh grid for x and y, I will have data that looks like 50 by 50 shape. Y will again be my 50 by 50 because the shape is 50. So I will be using a mesh grid and will populate x and y, and then I will be applying my hypothesis in these equation. So I have optimal value of theta, I have minimum cost. Okay, so I will be applying my hypothesis and will be getting the result based on this equation. And then I will use contour to plot my data. In contour I will pass x and y and then hypothesis. Yes, and I will do a visualization. So if you're not familiar with contour or mesh grid, I would recommend you to watch a separate tutorial on in more detail what mesh grid and contour does. Okay, so I will be creating a mesh grid, and then I will be using the polynomial 60-degree feature in this coordinate, and I will be using contour to plot the graph, to plot my output. So why I am doing this is because to show my visualization. In the reason for using contour mesh grid is it gives me an output in eclipse shape. Because my data is in eclipse shape, my admit and non-admit data is in eclipse shape, so I am creating a dummy set of x and y, and by using my minimum cost hypothesis and trying to visualize my data, how it looks. The reason for using mesh grid and contour is it gives me a circular eclipse shape equation so that I can do my visualization. So let's implement this. So my So let's say my initial theta is 1. Once x1 dot say, and my minimum cost is right now, let's say lambda is 1. Okay, as I said, my x as is, suppose I'm plotting and doing a line space, so where my x ranges from -1 to 1.5 to 50 times. Likewise, doing a ys, and now I will be using mesh grid. If you will see the shape of xx dot shape, it will have 50 by 50 because this is 50 by 50. So if you see the data, it will repeat all the line space that we have drawn from -1 to 1.5 50 times, 50 by 50 times. That's what mesh grid does. Now suppose my x data is, so we need to apply, so this is my x and y dummy data that I have created. Now I will be applying my map feature which I have created. So like I said, the reason for doing this is to visualize my result, so that if I use mesh grid and contour, I can visualize my result. It will give me an output that is something similar to Eclipse. So let's create a data frame first. So let's give a name. What the Rebel does is it flattens my output. Can check that. So then I will be applying, need to flatten the output, and then we will need to apply my map feature. Yeah, let's say this works out. This is working, and say my initial data is zeros of 1, and now my h theta is my hypothesis. So what would be my result if I get the minimum cost optimal value of theta, then what would be my result? Let's check that. This will be helpful while we do the visualization. So x data, this is what we have added feature, polynomial 6-degree feature. This is my minimum cost for lambda equals 1. So this way I will get hypothesis, and then let's reshape this to 50 by 50 because we have data 50 by 50 size. Okay, so we already did visualization for input dataset. This is my input dataset, and now I will be using contour. So let's use contour. So you can Google use of contour. So it takes input, and this will be x and y coordinate, and whatever the manipulation, like after manipulation we derive our hypothesis. So this all the manipulation what we did, we need to give in our third parameter. So do not show. So here we can see that. So my boundary line for logistic regression is, we know that it's 0.5. Let's go on 0.5. So here we can see that our model is performing really well when we give lambda equals 1. Okay, so let's create a function and if plot data and pass in coefficient here, and let's return minimum cost. So let's say if my lambda is 0. So this is my visualization. So let's say my lambda is 0. We have minimum cost. So we can clearly see a overfitting case here. Like we can see that it's been manipulated for every admit cases, and even small cases over here is being added. So this is while we use lambda equals 0. So this clearly looks like an overfitting cases where each output is being in predicted. So here we can see in the cases where we are trying to predict each and every output. So let's add accuracy. Even what's the accuracy? Let's check that. Minimum cost. Score. Here we see an overfitting issues, and if we and my accuracy is 87%. So if I use my lambda 1, here we see a good fit in our data, and our accuracy is 83%. And let's say if I increase my lambda to 100, here we see an underfitting issue where the model is nowhere out the admit and non-admit cases, and even accuracy is very low. So the example clearly illustrate that we need to use lambda as 1. This is giving us a perfect, not a perfect, but a good fit to our module. So that's the use of regularization, and we need to check lambda while evaluating our module. So right now we did we took 1, we can write a loop and check all the possible values of lambda and can do a visualization. So this is an example that shows the overfitting cases and how we handle overfitting cases by using lambda. So in summary, I would like to say, if we have more than 10 to 20 feature, we need to include regularization in our equation, and this will help us to shrink, penalize, we add penalty to our theta, so that it gives us the uh, good fit while predicting and implementing the module. So that's it for today's lecture. Hope you like my video. Please subscribe and encourage me to create more videos. Thank you so much.